In this episode of The Bear Roars, Dan welcomes Jun Ye, a world-renowned physicist and pioneer in precision timekeeping. Jun is a fellow at the National Institute of Standards and Technology, or NIST, and JILA, as well as an Adjoint Professor of Physics at CU Boulder. Dan and Jun dive into his groundbreaking work on optical atomic clocks, which earned him prestigious awards like the Yuri Milner Breakthrough Prize and Niels Bohr Medal. Discover how Jun's innovations, including laser-cooled atoms and optical tweezers, are redefining our understanding of time and its role in sensing Earth's movements. From quantum mechanics to the relativity of time, this conversation is a journey into the cutting edge of science and discovery. Let's poke the bear to kick off the conversation.
Professor Jun Ye, I want to say to the people listening how much of a treat they're in for. You are an understated person. If you go and look at your bio, it doesn't say all that much, but then you dig a little deeper, and it's just amazing what you are doing and what you have done and the recognition you got for it. And we'll come back to that. But I want to start with kind of when you and I first met, which was here at my house. As you reminded me, in 2019, I probably would have struggled to pinpoint the year, but that sounds right. And we had a dinner, and a dinner that, I can't remember the exact origin. I think I was doing something to sponsor, I know what it was. It was actually Dana Anderson approached me about sponsoring some conference they wanted to have. And I said, sure, but in exchange, I want to host a dinner and get some of the smartest people that we have around quantum to come to the house and just talk about whatever there is to talk about. And we did that. We had a big table full of the smartest people that I've been around in the area, certainly in the area of quantum, but in general. And they all would look at you at the end of the table saying that you're the man. Out of everyone there, you're the person that is the most accomplished. And in Boulder, at both NIST and CU Boulder, there's been 4 Nobel Prizes. And one of the Nobel Prize winners you worked for, which we'll get to, but they also referenced at the dinner that there's going to be a 5th Nobel Prize in quantum out of NIST and Boulder. And that 5th one eventually is going to go to you. And that's what they said at the dinner. So let's talk about a couple of the awards that you won just to kick this off. The 2 that caught my attention. By the way, I should also say to listeners, this is the only time I have notes for one of these podcasts. I did a little bit of digging, 10 minutes worth to be fair, but first time with any podcast guest, I thought it appropriate to just get a little bit more aware about their background. So the 2 I want you to talk about, and then if there's any other one that's special to you, please talk about that as well. But the first one is from venture capitalist Yuri Milner, which is a Breakthrough Prize in Fundamental Physics that you received in 2022, so very recently. And it was for your work in precision timekeeping or clocks. The second one is the Niels Bohr Medal of Honor Award. So tell us about each of those 2 awards, because those are big deals. Tell us about those awards, what they mean in general, what they mean to you, and the work that you did to get that recognition.
Yeah, thank you, Dan. The first prize that you mentioned, the Breakthrough Prize, was to recognize the development of optical atomic clock based on neutral atoms. This was an award given jointly to myself and to Professor Hidetoshi Katori of University of Tokyo. Mm-hmm. Back around the turn of the century, we came up with the idea that you can trap atoms in optical tweezers, but optical tweezers.
In the turn of the century, meaning?
About 2000.
So 2000, so the most recent century, so 24 years ago.
Yeah, 24 years ago. That's really how long has this optical atomic clock based on neutral atoms has been going on. And at the beginning, the atomic clock was...
Well, let's talk about what that means, because I've done 4 podcasts on quantum, and we've gotten pretty deep into quantum, but more from a layperson's perspective.
Yeah.
So I know a lot of people are following this, are loving learning about quantum. So when you talk about trapping atoms, talk about what trapping atoms means.
Right. So maybe it's actually interesting, if you don't mind, I go back a little bit,
Please.
Talking about your dinner first.
Yes.
And 2019, it was very gracious of you of inviting some of us from CEO Boulder to come over, because I remember that year very well. That was the beginning of the so-called Quantum National Initiative. And the CEO Boulder wants to be part of that leadership role in developing quantum mechanics into even more powerful workforce as well economic impact, and especially future technologies like quantum computing and so on, quantum sensing. And at the dinner table, there were two of my colleagues. One was my thesis advisor, Jan Hall. Mm-hmm. The reason I'm mentioning that name is because with Jan, I did my PhD and I learned a lot about studying spectroscopy, precise laser spectroscopy on ensembles of thermal atoms and molecules. Things are moving around. Atoms and molecules are moving around. Then I went on to Caltech to do a postdoc from 97 to 99. In that institution, working with Dr. Jeff Kimball, I learned how to control individual atoms. When I came back to CEO Boulder to take up the position at JILA, being an employee with NIST as well as CEO Boulder, I started to want to combine the two worlds where you have individual atoms, but I want to have many of them because one atom only gives you so much information. Imagine you get 1 million of atoms to tell you what time it is. That's certainly going to be more accurate or more precise than if only one atom can tell you that. But on the other hand, I cannot afford to have these atoms to be random. We want to get into this quantum game where each atom is controlled in the quantum state, in its particular quantum state or pristine quantum state, where we can prepare where they are, we can watch how they evolve, and we can read out with the most precision the nature has given to us. And that really led to this concept of developing optical atomic clocks with thousands of atoms confined in specially designed laser traps, where they are both internal degrees of freedom, how the electrons move around nucleus, as well as the external degrees of freedom, how these atoms are actually moving around in the laboratory frame are now all well controlled in the quantum states.
And how do you control them? You use lasers to control them. How do you control them? And maybe talk a little bit about the relationship between frequency and controlling the atom to the point where you basically freeze it into its almost no motion, and then are able to use it for the purposes that you described. Tell us how that works a little bit.
So at room temperature, the atoms are moving around with a few hundred meters per second. So basically, each atom is like a bullet train bouncing around.
Yep.
And so there are many limitations to that. One is they're going to collide with the wall, obviously. Mm-hmm. Also, they are moving around with a speed much faster than a person who's observing them. And we all know there's so-called Doppler effect from both first-order Doppler, basically the train moving towards you, you hear the whistle's pitch goes up. And as well as the second-order Doppler, which is Einstein's relativity theory, tells you a moving atom will be evolving with a different time than a stationary atom. So we want to get rid of
time.
Time is all relative.
Time's relative.
Time's all relative. Yeah. And as they say, move faster, live longer. There's some truth to that.
Yes.
But we want to...
And just to pause for a second, what you mean by that is when we say time is relative, if you're in motion, your tracking of time will fundamentally be different than someone who's, relatively speaking, in less motion. And that's a proven effect. It wasn't at all understood that something like that even existed till Einstein kind of conceived of this and then later proved it to be the case. And that was kind of the kickoff of a new revolution in fundamental physics. How does the world really work if time is not a constant that we all observe equally, but it's something that's relative depending on one's position and motion. Mm-hmm. So that's when it's moving around really quick and you're trying to observe it, you've got that effect to deal with.
Yeah. And also, if we are talking about creating quantum coherence, meaning something which is, say I have a pendulum. If I have electrons moving around the nucleus, it's moving super fast, but I slow down to play slow motion for you. It's like a little pendulum moving back and forth, like a quantum pendulum. if that pendulum is swinging around so fast, you couldn't hardly ever see how the pendulum is actually moving, then you cannot really do precision measurement on it. So that's another reason why you wanted this pendulum to be sitting right in front of you so you can study it for a long time.
Yep.
And I don't want just one pendulum. I want millions of them.
Yeah, but let me pause you there. So when we talk about slowing them down, motion is heat, right?
Yeah.
So motion is heat. So one way to slow down an atom is to make it real cold. And there's kind of a physics effect that allows you to do that with lasers.
Yes, that's correct. It's like refrigeration of atoms. You are correct. A thermal ensemble of atoms got a lot of heat in it. Another way of saying is you got a lot of entropy. Every particle is random. How do we go in there to make every atom behave exactly the same way? That means take all the entropy out or cool them down to very, very low temperatures or with very low motion or degrees of freedom. How do we do that? We use so-called laser cooling, where each atom you can think of as a little radio station. The atoms absorb light at a certain frequency. That's how, in fact, I love the metaphor that the light is how we communicate with the microscopic world. That's how we learn how atoms and molecules how they vibrate, how they live their life. We observe them through light. But then once you can observe them, you can also use the light to control them. And so the idea being, if the atom is moving towards you and you want to, please slow down, you're moving too fast, you actually take a photon machine gun, shoot against that atom such that as it moves towards you, it preferentially absorbs the photon from ongoing photon machine gun that I'm shooting against it. And therefore absorbs this photon momentum from the incoming laser beam. And then when the atom rescatters the photons, it rescatters from 360 degrees solid angle. Therefore, the momentum that's outgoing is averaged down to zero. Therefore, the net effect is you have taken incoming momentum slow you down. Now you may ask the following question. How do you know the atom is moving towards you? Some atoms moving away from you. Some atoms moving sideways. How do you make sure all of the atoms in the end can be slowed down? Well, we actually do that by shooting 3 pairs of laser beams along 3 orthogonal spatial directions. And their frequencies are all tuned at a specific value when only the atoms that moving towards that particular laser beam preferentially absorb the photon momentum kick towards backwards, such that you're always opposing their motion. And we can do that now routinely. We can actually teach this to undergraduate students.
Oh, wow.
It's a very powerful, you can even see with your eye. You can look at the atoms are moving around, and then when the laser cooling turns on, you will see a little light bulb turns on in the middle of the vacuum because all the atoms now are being collected into a very special, a specific spatial region. They are fluorescing, and you can see this as a little bulb.
So when you think of a lattice, that's what you're really referring to. You're putting each atom in a spot in what we would call a lattice. You're kind of arranging them into space where you can then prepare to do other things with those atoms, measure certain properties as well as trigger certain interactions between them. Is that right?
Yeah, actually, Dan, the lattice is actually the second step. So we do cooling. We make atom really cold.
Really cold.
Where they are moving much slower than an ant can crawl. So going from bullet trains to much slower than little ants is moving around. But that's not enough. If you let them go, if you stop cooling laser, these atoms will fall under gravity. They will still fall onto the surface of bottom of the vacuum chamber. So we have to design something called an optical trap. So we have optical cooling that's made by laser, and we then follow the initial cooling step by the so-called optical trapping. The optical trapping is what you mentioned as optical lattice, where we interfere laser beams. And now we are talking about different lasers now. It's no longer the laser that tuned to absorb photon momentum, but rather a laser which is tuned far off resonance of the atom, but it can still have reactive sort of force on these atoms where you can trap these atoms towards the center of the focus, where the intensity is a maximum. So you create these standing waves optical lattice field, And if you create a three-dimensional lattice field by having three different pairs of lattice along three different directions, you can create a little bit of a kind of artificial lattice. Looks like an egg cartoon if you want to.
An egg carton.
Egg carton. Each individual egg is like your atom, and they go into each one of those cartons.
So, if you picture a big egg carton that maybe has 6 one way and 6 the other way, you have these atoms sitting in each of them.
Yeah.
So you're preparing them. You're preparing them to be in a certain space. Collection of them. Think of it as maybe even like a grid. You're putting them in a spot on a grid by using these different laser techniques.
And in fact, one of the biggest, I would say, quantum revolution that's happening right now is to scale up these quantum systems. You mentioned by 6 cartons and so on. We actually make millions of them. Mm-hmm. Imagine you can capture millions of atoms. And maybe another question may come to your mind is, how can you be sure that only one atom sits in one location? How come you don't have 2 atoms, 3 atoms on there? But we can tell. Sometimes we have 2 atoms in the same site, 3 atoms on the same site. We can actually control that. We can make sure that only one atom and only one of them sitting in one particular location. And every location is filled with one, but only one atom.
Yep.
And it's an incredibly low entropy system.
For the first time, Dan Caruso pulls back the curtain in his book Bandwidth, a memoir that celebrates the pioneers who invented the internet's early backbones, the renegades who lit the fiber revolution, the antics that caused the biggest market crash of all time, and the new wave of entrepreneurs who led the industry back from its ashes. Though it seemed to happen in the blink of an eye, the Bandwidth adventure was a multi-decade roller coaster ride involving larger-than-life successes and devastating failures. The unbridled ambition of newly minted billionaires and high-profile tycoons created extraordinary value, unprecedented value destruction, and endless opportunities for a brave few. This reflects tech's past, present, and future, and is a story you won't soon forget. It will help you prosper during today's AI tech bubble. The book is available for pre-order at dan-caruso.com/bandwidthbook and released in early 2025.
Yeah, so I'm going to take us on a tangent, and then we're going to come back.
Yeah.
The tangent I'm going to take it on for the people listening in is why it matters that you're doing this stuff. Like, what are the real world possibilities that are taking these scientific breakthroughs that the team there has been making and is continuing to make? What do they do with them? So maybe talk about everything from timekeeping to different sensor applications. There's the methane detector. There's GPS replaced by QPS. Talk about how certain types or modalities of quantum computing rely on these techniques. So what will this science lead to? And then what we're going to do a little bit later is we're going to talk about not the real world applications, but the scientific understanding, like what this is leading to greater understanding of how the fundamentals of nature really work and where that's headed, and what this type of science, has revealed and is likely to reveal as we look forward.
Yeah.
So talk about some of the commercial aspects of implications of the work that you're doing.
Well, if you have the capability of arranging atoms, one by one, essentially, you are making your own material. You are making an artificial material, and each atom can be prepared in a particular quantum state now, because they are no longer moving. You have all the time in the world to prepare their quantum states. All of the atoms are identical. So once you can achieve that, that's your quantum resource. This is the quantum platform. You can use this to tell time. You can build clocks based on this. You can use it to build a quantum computer. This is exactly now some of the leading platforms of quantum computer, because all these atoms are sitting right in front of you, and you can prepare their initial quantum state. You can turn on how they want them to interact, and you can read off so-called quantum gates. Mm-hmm. And
you were, or maybe still are, a advisor.
Yeah, for atom computing.
For atom computing, which is
exactly this technology.
We're an investor.
Oh, wow.
Atom computing just had a major recognition of their work through Microsoft.
Exactly, yes.
Yeah, so Microsoft made a major announcement at the CEO level of Microsoft, believe it or not, announcing kind of their collaboration and the advancement of the neutral atom,
Yeah.
old atom-based quantum computer that you're describing.
That's
They're not
correct.
the only ones doing that, but certainly they're one of the leading ones in a field of maybe 5 or 6 companies who are, prominently doing this.
Well, I can say that one thing I'm really proud of is that the founder of that company is my former PhD student.
Yes, Ben.
And Ben Bloom picked this particular atom, strontium or ytterbium. That's the atom I use for clock. So Ben learned how to build atomic clock, use this particular atom, strontium, and he felt this is advantageous compared to alkali atoms, where the atoms in the first column of the periodic table. The atom that I like to use sits in the second table, and it's all because of the technical details of the quantum coherence and so on. So Ben's company right now is I believe among the leading companies, the only one that's really using the alkaline earth atoms to build a quantum computer with it. And it tells you how fast the field is moving, right? IBM, you mentioned, they were all banking big on superconducting circuits. But then they realized, thanks to my colleagues at Harvard, like Michel Lukin and so on, start to work out these neutral atom platforms.
I didn't realize IBM's starting to explore neutral atom. That's a big deal because they were pot committed big time in the superconducting.
Maybe I misspoke. So the Microsoft.
Microsoft.
Yeah.
Yes, Microsoft.
Yes.
Yeah, and it's still competing. The neutral atom method for computing is still competing with other methods or modalities.
Absolutely.
Including Google just had a big announcement. It was just last week on some breakthroughs that they're claiming on the superconducting modality.
That's correct. Yeah. I mean, they each platform has their different advantage and disadvantage. What a neutral atom system that's coming along is it's moving super fast in terms of initially the fidelity was not as good, but now the fidelity is really catching up on the single qubit gates or 2 qubit gates. And what the neutral atom has to its advantage is the technique I was just describing to you, how we can trap these atoms on a tweezer at the end of the optical trap. It turns out the optical field, it's much easier to rearrange them instead of rewire. In superconducting circuits, you have to rewire with wires. But here, photons is your wire, and you can reconfigure the atoms at will much, much faster. So the scalability in the future, neutral atom holds a lot of promise.
Right. So let's go back to the timekeeping. So there's numerous methods being explored for computing, including neutral atoms. But when it comes to other fields, quantum sensing, neutral atoms play a much more clear role.
Yeah.
Most of the other methods for quantum computers don't apply to sensing applications. So let's start with timekeeping. I wear an Apple Watch. I could tell the time.
Yeah.
Why does it matter that neutral atom technology science is going to be applied to timekeeping? Why should the world care about that?
It's kind of interesting to think that you got it exactly right. When you talk about measuring something fundamental as time and so on, as space, well, you wanted to use particles that's made by the universe itself. If it's made by human beings, it's very likely things will be different. I make my superconducting circuits, you make your superconducting circuits. Our frequency will guarantee to be different. But atom was created at the Big Bang of the universe. They were all created equal. And so in principle, this is exactly the standard that we want to have. It's a standard of nature. And if you do your experiments right, whether you do it in Boulder, Colorado, or whether you do it in Washington, D.C., and so on, it shouldn't matter. Wherever you do the experiment, they should give you the same answer. And in fact, they probably won't because the geopotential, the potential is different, but that would turn into a real quantum sensor. So and that's where your statement of why suddenly, by the time you get to the quantum sensing, neutral atom plays a much, much more important role because neutral atom represents the nature's qubit. And it's being made that way, and we're just going to take advantage of it.
Yep. And why do we want more precise time? What are some applications that will come out of? Because the most the most accurate timekeeper in the world
Yeah.
still is up there in NIST. Is that right?
Yeah. At the moment, the definition of time is still based on the so-called microwave clock. That's because of all the infrastructure that's been developed over the last several decades. But the new kind of clocks that's coming along is now much more precise. And it can be factor of 1,000 or 10,000 times more precise than the current system that's defining the time. So there's a lot of discussion now in the scientific and meteorological community of redefining time based on the new generation of optical atomic clocks. And why do we care for a more precise time or more accurate time? Was for several reasons. I think one is human curiosity. I think we are always curious. Can we build the most precise instruments that human beings can ever make, such that we can use this to probe the deeper universe? There's still a lot of mysteries out there that we do not understand about the universe. If we continue to build instruments that can measure time and space super accurately, this will turn into a very sensitive probe of nature itself. Mm-hmm. The second, and
I'm going to want to come back to that topic and go pretty deep into it.
That sounds
later
good.
In discussion.
Yeah, that's fun.
Yes,
but on the other hand, I always say there's another aspect is, as a human society continue to advance, though we are networked ever more so than before, synchronization of modern society becomes very important, not just communicating with each other or navigation and so on. Later on, we may want to have a GPS system for the entire solar system so that we can colonize other planets, or we can go to other places other than just Earth to call our home. So we're going to have space navigations. We're going to have all the unmanned vehicles that's going to be flying or moving around us. We are going to synchronize all our banking, communication networks together, and more precise time allow you to do that.
Including data center environments.
Exactly.
The data center environment's one of the constraints of how much data can you fit in a certain amount of material.
The channel capacity. Exactly.
Communication networks, as you said, financial trading networks. So the more precise the time, we could up-level these systems to create new and interesting technology.
Yeah.
Most people who use them and benefit from them won't really know what's going on, but what it will be is the incorporation of neutral atom technology in our everyday world, playing many roles. Now, you also made the comment that we could use it to know the precisely synchronized time between, you used as an example, Boulder and Washington. And then you said, but there'd be a slight variation. But that slight variation would be unveiling some data.
Yeah.
Unveiling something else going on. So that's where the timekeeping starts moving into other sensing applications.
Of geology.
So talk a little about what you meant by that.
How the continents are changing. That's because time. So we mentioned the first principle of Einstein's relativity, the so-called special relativity, where different moving objects may from a proper observer that's being stationary in the laboratory, when particles are moving around, the time is different. Mm-hmm. But there's another so-called general relativity that at the different elevations, because of the Earth, gravitational field of the Earth, and as well as the sun and the moon, our time is all different depending on the gravitational potential. And now we're talking about space-time curvature here.
Yes.
And so time, if you can measure time exceedingly accurately, then you will be able to sense where you are. You might be able to see how the mass is moving around you, how the overall continental drift, or maybe the east coast and west coast of the North America is dancing around, and we never have had that technology to be able to really see what's going on. So it becomes an incredible sensor of our environment.
Yep. And
maybe in the future, could it be a useful technology to predict volcano eruption, to predict earthquake and things like that,
mm-hmm. As well as using it to sense materials that might be buried deep into
mine and
Europe.
minefields and so on. Yeah,
minefields, but also maybe valuable rare earth type of minerals, or if you apply it to space, finding kind of where to look for valuable materials buried on the moon, as an example. So, talk a little bit about what field that is, where you're kind of using it to sense what's happening kind of underground.
Yeah, and so this is really talking about huge amount of commercial potential right here. So, I'm a lab guy. We do experiments in our laboratory, but for clocks like that to be truly useful, you need to take this out of the lab. You need to build a network. That's why your initial connection to us was very valuable. You are a pioneer in fiber networking. We need to build networks of fibers or even air links between different clocks, so clocks can be distributed. And you can actually measure the time differences between these different clocks. And that will tell you, maybe it will turn into a gravitational wave observatory, just like LIGO has been able to now turn this interferometry readout to tell you which black hole has exploded, what neutron star is being spiraled in. This turns into this incredible astronomical observatory. And if we start to take those clocks out of the laboratory, which requires a lot of engineering to make them compact, smaller, robust, and connect them up by sending laser beams across the sky or between the satellites, or using fiber links underneath the ocean so that we can compare these state-of-the-art clocks at a level much beyond our current timekeeping, then these really will turn into an incredible sensor for space-time.
Yep. And one early application of that uses the technology is a Boulder-based company that traces its roots back to CU and NIST that is called LongPath. So LongPath is using, some variation of what you're describing to detect methane. Mm-hmm. I assume you're familiar with LongPath and what they're doing?
Yeah, absolutely. Yeah.
So tell us how that early application of quantum sensing, what's really happening there, and how does that relate to the work that
So LongPath is not connected yet to the time distribution, but LongPath uses a tool called a frequency comb. And the frequency comb is a tool that's invented by the gentleman who had a dinner with you. We were all together. I was his student, Jan Hall. We were working together to develop these frequency combs. The original purpose was to connect the optical frequency that we are using lasers to read how the electrons are moving around nucleus. We need to connect that frequency down to microwaves so you can connect to your watch. Mm-hmm. That's how optical frequency comb was invented for its only original purpose. But once you have a frequency comb, you realize, okay, this turns into an incredible tool that can sense molecular absorptions. And in fact, I would say, actually, my group was among the very first that wrote the first few papers on how to use frequency combs to do spectroscopy. Mm-hmm. And that's because you got a massive amount of lines.
And spectroscopy, tell us what spectroscopy is.
Spectroscopy is basically tell you, spectroscopy is to find the signatures of atoms and molecules. Atoms and molecules communicate to us through a unique set of fingerprints, which is what particular color they absorb light. And the spectroscopy is just trying to figure out what molecules are absorbing what light.
So just to break that down a little bit, you use the expression fingerprints because we all know that each person has a very unique fingerprint. And if you know their fingerprint, you know the person. And then you use that to say that each type of atom, would that be the right word? Each has its own signature.
That's exactly correct.
In terms of a very precise frequency of light that they emit. Is that the right way to put it?
That's exactly right. This is exactly like a few hundred years ago. That's how people figured out there's a helium or hydrogen in the sun, because they can actually watch the sunlight as certain black lines, and that's because the atoms are absorbing. And so spectroscopy, I think it's since dating back to the time of Newton. By looking at the spectrum of light and watching at a particular color that's being absorbed away, or molecule casted a little shadow. Each molecule has its own unique set of shadows. Yep. And that's how you can identify molecules. And you can actually use this to also study quantum mechanically how molecules are constructed. It's actually very powerful. I would say spectroscopy is really laid the foundation of modern physics.
Yep. And the expression comb, frequency comb, you think of a comb that has the different, I don't know what you would call those coming out of the comb.
It's particular components, right? The comb is just a very visual way of thinking, okay, I use comb to comb my hair every morning, and a comb has a very special tooth, and that's very regularly spaced. Mm-hmm. Now imagine in a fictitious landscape, which is a frequency, and we have a frequency markers that's evolving exactly regularly as the comb would display itself, so that a rainbow of color. If you break that down of the color, you will see digital colors one by one, and their spacing is completely regular, and that's why we call it a frequency comb. It's a tool that was invented, as I mentioned, to connect optical frequency to radio frequency. But now you can say, once I have that comb, once I have that rainbow, I can use this to sense what's in this room. What are the molecules in this room? Because I can cast the light through this room and find out what shadows these molecules are leaving behind.
And the way LongPath is leveraging that is they're putting on towers, the equipment that I assume is blast. One side there's a frequency comb, the other side there are lasers. They're blasting them over a wide area, and they're looking for signs that there's methane concentrated in a particular area.
Yeah. If
there's methane concentrated, so basically the frequency, the light emitted by methane molecules kind of triggers, they can say, we know that there's a methane leak right in that particular area, go fix it. Mm-hmm. So one early application of this technology, so when people think of how difficult everything you describe, we're going to control a bunch of atoms, we're going to do all these things, and it's going to lead to these breakthroughs in how the world works. The early stages of that are already showing signs of commercialization. This isn't pure science in laboratories.
Yeah.
We're already seeing the beginnings of this being applied in real world commercial applications.
Yeah.
Which is fantastic.
That was the third thing I was going to say. When you were earlier asking me why do we care about more precise clock, it's precisely because of this. As we chase for the absolute best, we are developing technologies that we don't even know that existed, of course. And we have this very much goal-oriented way of developing new technologies. But in that technology, because you're driving into the unknowns, you're driving a boat into a stationary lake, and you're going to leave behind a bigger wake of waves. And I use this analogy to say there are a lot of spin-offs that you cannot really say that you can all imagine all of them. And so the frequency comb is a small component for the optical atomic clock. It's just a one component. Mm-hmm. We talked about laser cooling, we talked about lattice. Frequency combs, just in some sense, it's a readout device. In the end, I have my light pendulum that's swinging by all these quantum state controlled atoms, and I need a frequency comb to finally tell me the link on the pendulum.
Yep.
But as we talked about, frequency comb alone can have many applications. Another one that maybe we can delve into later, if you're interested, is I'm actually now using frequency combs to measure people's breath. And we can tell, what medical conditions you may have.
Yeah, I remember when I came by your lab a couple years ago, you were showing that to us, and part of that was potentially detecting COVID just by breathing into a tube.
And we succeeded in that. In fact, it was very accurate. We published a paper in medical journal for the first time in my career. A paper showed up in medical journal about using frequency combs to smell people's breath to tell you whether you're COVID positive or negative. And now several medical doctors in CEO Anschutz heard about this, and we are doing very active collaboration. We are looking at the lung cancer patients. We are looking at asthma versus pneumonia patients. We are looking at COPDs. With the goal is to develop early detection capabilities. By the time somebody has got lung cancer, it's too late, right?
Mm-hmm.
And modern medicine don't require us to tell them if somebody already got a cancer, we don't need it. They don't need us. If somebody already has a COPD, they don't need us. But they tell us what can be very powerful is to very early on, just by monitoring people's breath, that can tell, okay, maybe you should be watching out. There's certain trend in your breath, in the breathing of your molecules coming out of your physiological system that you might want to be careful. And so if this turns out to be truly generally applicable, this is going to save society so much more energy and basically improve people's life.
You got to be proud of that.
Yeah, I would be very proud of that. Yeah, absolutely. And it's not a quantum 2.0, it's quantum-derived technology, but it's just like you mentioned the methane, long past being able to monitor our environment with a frequency comb. I want this to be also part of the medical science. It's a sort of a future of medical science.
Yep. And it's also for detection of, we walk into stadiums now and there's...
Yes, exactly.
So
the loom.
You could...
We can actually see, in fact, as we were studying now, the Children's Hospital, the director of research of a Children's Hospital is sending us the samples of children and want us to diagnose whether somebody's got asthma or pneumonia, bacteria or viral infection. And we also collect hospital samples of air so that we can tell the difference between patient's sample and the environment. And we can see all kinds of air in the hospital. If nothing else, you can use tools like this to do indoor monitoring of the environment.
Incredible. And maybe quantum radio frequency, quantum RF. Is that an area you're knowledgeable about?
When you say quantum radio frequency, you're talking about radio frequency detection. You're trying to see small radio frequencies, or
I'm actually looking maybe a little bit past that and thinking about communication networks, wireless mobile communication networks that leverage the wide frequency that can be used to do a 7G. We're on 5G now. Maybe it's not 6G, but looking forward 7G networks built out of it.
Yeah, so certainly optical communication, maybe not necessarily entanglement, quantum, and so on. The entanglement in the quantum network, I think, still has very specialized use of it. For example, if you're trying to construct very, very, very faint signals coming out of distant galaxy, and you want to reconstruct the exoplanets from distant galaxy, then use quantum entanglement and photon distribution is useful. But if we just want to do very large capacity communications, a frequency comb can actually be a very useful tool because it provides exceedingly compact form of very regular channel regulation. And so you can jam pack lots of information in there in the frequency comb. And again, I wouldn't say this is something require entanglement or anything, but it's just optical technology that's moved forward to support the quantum. And that provides these extra benefit that we can have.
Yep, fascinating. So let's get back to where we were before when you were talking about the developments and how the science works.
Yeah.
Let's see, when we left that off, we were talking about trapping the atoms, first cooling them down, then trapping them in a lattice.
Yes.
Let's move forward from there. Then what kinds of things do you want to do with those atoms or to those atoms?
Yes, exactly. So we were talking about once you have that resource, and when the atoms are individually packed into their respective trapping potentials, you created this unique material. If I may call it material, it is true. A quantum material that you created, you can use as a resources for metrology, for computing, for storage of information, and so on. But also, it actually provides a very interesting, deep insight about how real material actually behave. You hear about superconductivity. You hear about magnets. Where does a magnet come from? How do certain material that can have a zero resistance at a high elevated temperature? Imagine we have superconductivity at room temperature. That's going to save the world so much energy, right? And so these are all.
How will tell people will that save the world so much energy? Superconducting,
because you can then you can you can send electrical power from one location to the other without ever causing any heat if there's no resistivity. So 100% of the energy from the generator to a user can be delivered. And so majority of that.
Today, roughly how much would be lost because of resistance?
I think it depends on the technology these days. I think both US and China are now developing the so-called high voltage. Instead of transmitting through low voltage with a lot of current, the current turns into heat because of the resistance. But if you turn this into very high voltage and then you transmit through high voltage, you actually have very little current, and that actually uses less power. So there's this kind of technology. The energy is for modern society, it's all about energy.
Yes.
And so we wanted, whether you there's a lot of debate how we generate the energy, but there should also be a lot of motivations for how we transport the energy, how we store the energy, and then how we use the energy. Superconductivity will just allow you to transport energy with no cost. It would be amazing.
And what about storage?
Yeah, storage is yet another, people talk about batteries, people talk about certain countries with lots of lakes, they actually pump their water up to the mountains, and that's a very efficient way of storing energy. And then when you need it, you just release the water coming down, convert back to the electricity. But maybe we are distracting a little bit. But coming back to the same point, that the reason why these atoms in lattice is so interesting is, well, you can actually control how they can. And when I mentioned that there's only one atom per site, but an atom wants to tunnel. In quantum mechanics, there's a word tunneling. That's not very classical kind of a sense. But if in a quantum mechanical world, I can go through your wall. I can tunnel through the wall.
Might take you a few years.
Yeah, it might take many years. Probably never possible in the lifetime of the universe. But if I'm a quantum mechanical wave function, I can actually do that.
You do.
And I do. And we actually study this all the time.
So tell people what tunneling means. I mean, that's a good illustration. It's actually instead of being where you expect it to be, it tunnels into a different location, and it could be theoretically any location, but there's locations that are higher probability, and there's locations that are extraordinarily remote.
Classically, would be forbidden. For example, if between you and me, if suppose there's a big wall between us, and classically, unless you lift me up, just throw me over to you, I will never be able to get to you because the wall is going to stop me. But the tunneling in quantum mechanics, if I'm a quantum particle, I have this wave function. In principle, I can go through the wall and be on the other side with certain probability. And we can study this in this.
And you're saying in principle, but in reality, it happens all the time. Tunneling is just a quantum phenomena that's playing out all around us all the time.
Yeah.
It's just not at the macro scale that we live on.
Because we are not a quantum mechanical wave function.
Yeah.
So at a single atom level, certainly at the photon level, at a certain atom level, when I have these atoms in individual optical lattice wells, if I only put one atom in one lattice well, this atom, if you wait for a little while, you will find this atom lives somewhere else. And that's because it's tunneled. Imagine your egg, you put an egg in egg carton, and next morning, this egg is somewhere else. And you will find it very strange, right?
And it didn't move there, right? It wasn't that it found a way to move from one spot to other. It just was no longer here, and it's now there. Is that the right way to think about it?
Yeah, so you can think of the wave functions basically spreading itself out. And the probability when you make a measurement, you collapse the wave function at a particular location.
Yep.
And so has these kind of sounds like a science fiction, but it's not. You are exactly right. These are real phenomena, and we can actually there's real consequences to material. If I have two atoms on two well, in principle, when I say in principle, but in reality, actually, this atom can jump over on top of the other atom and sitting on top of each other. But then the other atom says, "Go away! If you come here, we are too crowded. I have too much energy. Please go back." And when you do that, you'll find sometimes it's the original atom was kicked back. So it's like two atoms has exchanged their position.
Yep.
And these are the phenomena we observe in the laboratory all the time. So the reason I'm saying this is, well, here I am. I'm trying to build a clock with atoms in this three-dimensional lattice. But now, yes, we can use this as building a clock. Yes, we can maybe turn this technology into a quantum computer. At the same time, it's actually developing some deep insight of how material actually works at the quantum level. Is that fascinating? This is something, that's what I always say, quantum mechanics, the quantum technology we deal with today is a continuous spectrum. Whether you want to build a quantum sensor or information processing or material science, turns out it's the same quantum technology or quantum weirdness that's governing all these.
Yeah, so we talked about tunneling. There's two other properties, one of which you touched on, one of which you mentioned, but there's really, as I understand, there's three properties that make quantum weird. Mm-hmm. One is tunnel, one's superposition, and one's entanglement. Mm-hmm. So we talked a little bit more about tunneling. Talk about the other two and what those really mean. What does superposition mean?
The superposition, there's in quantum mechanics, we use the word quantum state. And I know that's not very meaningful in a lay language. Or another way of saying is there's certain
properties?
Certain property, maybe that's the right word, certain property of quantum systems that seems to be stationary. You can say you have a quantum particle. You said you are in position A, and so that quantum particle can be in position A forever. But it can also be in position B, and it can be there forever. But at the same time, you can create a superposition of position A and position B simultaneously. And then this quantum particle is in a indeterministic state. When you try to make a measurement, are you in state A or state B? You can never be certain. This is a fundamental properties of quantum mechanics. And in fact, quantum mechanics is really when I give a talk about clocks, I always say the very reason we can build super accurate clocks is because of quantum physics, because electrons has a prescribed orbitals around the nucleus. Classical mechanics doesn't have that. But at the same time, the very reason that the quantum mechanics also limits our precision is because when you prepare the atom in a superposition, it has intrinsic indeterminism to it. You don't know whether it's in state A or state B. It's in superposition. Yeah. And
so it's not that you can't determine it, that you don't have the measurement capability to determine it. It's that no matter how precise your measurement is,
you perturb that quantum state. Yeah, exactly. You perturb that quantum superposition. So this is really the fundamental nature of noise. Really can trace back only through quantum mechanics. The only thing that's truly is indeterministic in this universe is due to quantum. Mm-hmm. And no wonder some people want to say free will is because of quantum. Some people like to believe that.
Yeah, philosophy. if you're thinking about philosophy and how the world works, and and what other things might be happening around us that we can't sense, it always comes back to these properties in quantum and what they might not just really mean, but what you might be able to do to harness them. As we get more and more advances in civilization. Mm-hmm. So tunneling, superposition, and then there's my favorite, which is entanglement.
Now, the entanglement actually, in some ways, I think requires you to understand first the superposition, this intrinsic noise. Mm-hmm. So let me take another example. If you have a coin, classical coin, it's not a quantum coin. Say a classical coin, it's got a head and tail, and the quantum coin is actually much more sophisticated. It's not just head, tail. It can be anywhere in the middle. But suppose I visualize a classical coin at the moment. You have a head and tail. You put it in superposition, meaning this coin is spinning, and you don't know head or tail. And you will say, oh, how is that? Doesn't seem to be weird. A referee in a football game throw a coin up in the air and they say head or tail. Seems like very random, but it's not. As soon as the coin is going out of this person's hand, its state is determined. Mechanically, we can calculate everything. And the only reason why it appears to be random is because the referee did not do that calculation in his head.
The math's complicated.
Math is complicated.
But also, that's only true if you live in a classical world
Yes.
completely.
Yeah.
So if it's a
But
completely
in
classical
quantum,
world, it's
you
classical.
really don't know. You really don't know whether it's head or tail. Now, if you take that as quantum awareness, if you are
So let me
willing
just
to
pause
accept
you
this,
there. When you say you really don't know, and no matter what calculation you could do to that,
that's right.
you could
You can never know.
So it's not because you're unable to calculate.
Yeah, exactly.
It's that
It's
it's
in
because
principle,
it's
you do not
unknowable.
know.
It's unknowable at that point.
Yes.
Okay, so
now what about entanglement? The entanglement, actually, in the simplest possible way to think about it is, okay, I have two quantum coins. Each one of them is unknown, and you cannot know.
Yep.
But if there's entanglement between them, then if this coin happens to have one particular state that's being revealed, the other coin will also have its state being revealed at the same time.
Yep.
And the entanglement gives you such a strong correlation, such that instead of having two copies of a noise, like each particle has its own noise, right? But when you have the two particles entangled, you have now only one copy of noise, because only one randomness of the coin determines both.
So if you were a gambler and you wanted to rig the system in call it one room, you're making a bet and you're saying, I'm going to flip this coin, and I'll bet you I know whether it's going to come heads or tail.
Yeah.
Now you have your buddy, unbeknownst to
other people,
yeah, flipping the entangled coin in another room.
Mm-hmm.
So now those coins flip, they both hit,
Mm-hmm.
and your buddy all of a sudden sitting there in another room,
knows the
knows
information
with certainty, that it's tails.
Yeah, that's correct.
So now he has to tell you.
Yeah.
So how does he tell you? You have a wire.
You still have to have a wire. So the communication
Yeah.
still has to go through speed of light. So there's no instantaneousness there. But nevertheless,
but your buddy can kind
information is secure.
Your buddy can send you a signal over kind of, something in your ear saying it's tails.
Yeah.
And, you're able to kind of, win the bet, rig the system.
And what you just said is basically lie at the heart of the quantum communication.
Mm-hmm.
That's the quantum key distribution, the cryptographic way of communicating to have information to be completely secure. And that's really lies, this single understanding of how entanglement works is because of the uncertainty principle become correlated between two different particles. And that's very powerful. And in fact, this is the same fact I use to try to build a better clock. I use 1 million atoms, for example. Each one of the atom has noise on it. So if I have 1 million atoms, meaning my uncertainty would be square root of 1 million. That's 1,000 to 1. That's just because the noise is scales with a square root of the number of particles you use. But imagine these 1 million particles are all entangled, and you have only one copy of the noise. Suddenly your clock is 1,000 times more precise than if it's unentangled. So you can see, the advantage you are trying to gain from quantum metrology and advantage you are trying to have on quantum communication. It's the same thing.
Mm-hmm. And quantum computing
and
as
quantum
well.
computing
Using,
as well. Yeah,
yes.
Exactly. Yeah. So it's all connected. And that's why entanglement is such a useful resource for us to have. The entire quantum 2.0 is all about entanglement. Mm-hmm. But entanglement is very difficult to maintain. It's actually not difficult to generate. But once you generate it, it's actually not easy to inject into something, a useful device where the entanglement is being maintained over a long period of time, long coherence time, so that we can actually use it for doing metrological purpose or communication purpose and so on.
Yeah, but that's probably an engineering question, because we observe in the universe particles that have been entangled for long periods of time, that are coming from distant places as entangled particles, as I understand it. So nature
has entanglement built in. Even molecules. You can actually look at a molecular bond. You can say, these electrons are anti-correlated or entangled and so on. So nature has a lot of entanglement built in. And what we want to do now as a human society is we want to generate entanglement on demand and then use it in certain tasks that we want to have. So again, kind of along the same scientific development of the human civilization is once we understand how nature works, then we want to take over, kind of want to generate and use it for a special purpose. For our case, that I think you be a little cautious saying that's just engineering. At certain aspects, that's
maybe
true.
Hundreds of years of engineering.
Yeah, exactly. Certain aspects, that's definitely true. There are still certain aspects, especially you'll say, I have to process, I want to build a quantum computer that can solve the universe problem. In principle, and again, I use the word in principle because if you can control every single quantum particle, you put 1,000 of quantum particles together, and you can say, I can manipulate their quantum state, I can turn their entanglement on and off. You can solve the entire universe. You can really just calculate the universe, how that should be evolved. That's why some people believe we are living in a simulated universe, that God is calculating all these things. But on the other hand, it's not clear that we will be able to always have these error-free. As you flip those gates, they can sometimes have errors. And how do you correct for these errors? You will need extra resources of quantum bits. Whether you can outrun the resources, that's, I think, I tend to be optimistic that this will work. That we are just at the very beginning stage of error correction and so on, but it's not completely clear or scientifically that this is done deal. This may require new platform. We talked about superconducting circuits, trapped ion, neutral atom. We don't, maybe photon also, photonic quantum computing. Yet to be seen. Maybe there's new platforms that would be developed in the coming decades that would take over.
I mean, with classical computers, the technology changed, significantly. Decade over decade, and there's no doubt with quantum computing,
we'll do the same.
The specific technologies will change, but quantum computing isn't just an extension of classical computing. It's a different physics altogether. Let's go on a different tangent, and we're still going to come back to the big topic of kind of scientific study, but talk about JILA, talk about CU Boulder. Why does this geography play a special role in quantum? What has happened in this geography? What kind of discoveries? What's so special about Boulder and Colorado in general when it comes to the field of quantum?
Yeah, I think part of the reason, I think it has a lot to do with NIST being here.
And NIST is who is your kind of employer.
Yes, that's right. I'm an employee of NIST.
And how would you describe that? You're a fellow of CU Boulder, but a professor at NIST, or what's the right terminology?
Yeah, I'm a fellow of NIST.
Fellow of NIST.
And a fellow of JILA. And JILA is really a joint institute between NIST and the CU Boulder.
Gotcha.
And this marriage was formed in the 1960s. And Jan Hall, who had dinner here with me, and Eric Cornell, those two were Nobel winners. And Jan was actually the very first generation of scientists came from Washington, D.C. and established JILA here. And this marriage between NIST and the CU Boulder has really worked magic. On one hand, we are on university campus, right? We are ordinarily, you wouldn't be able to tell I'm a NIST employee. I'm just a CU professor. And I take on students from CU Boulder from all over the world, the best students coming, the most talented students. And I think that's actually the best ecosystem I can think of. Colorado quantum ecosystem is a lot of talented students who wants to come here to study quantum physics because of this long time, sort of excellence of a scientific tradition. And so on one hand, you're kind of in an open, almost said open quantum system. I meant to say open intellectual system, right? And you have a young blood coming in all the time, just the attitude, well, I don't know what's not possible. I'm a young person. Anything is possible. And so it's really amazing, kind of this attitude of learning new things, and you learn from the very best. At the same time, NIST provides some long-term vision. And I'm a NIST employee. In some ways, NIST has never placed any limit of what I do. On the other hand, I also know NIST has this mission, which is how do we develop fundamental scientific understandings that will help maintaining standards for commerce. It's actually quite interesting.
Yes.
So for commerce, you need the standards.
Need standards for commerce, dating back to, eons ago. And, how do you measure how much your precious material is worth? You've got scales. And
you've got scales. How do you trade your grain? How do you sell your wine? And it's kind of sometimes mundane, but it really comes down to it's a form of science. How do you making sure that we are using the same amount of electricity so we can charge people fairly? How do you measure an electron by electron and then turns into how many wattage you have used? And it's kind of amazing to think about time is another thing. It's a unit. It's a standard for people. And how do we develop best science to underpin the best measurement device? And that's kind of a NIST mission. So I always had this little connection to it. And that I always credit NIST for this particular aspect of, yes, I'm doing all kinds of research and I let my mind go free. Sometimes, we talked about using comb to measure medical conditions and so on. But fundamentally, my research always traces down to, connects back to measurement science. And it's because of a NIST's fundamental mission is advancing measurement science.
Yep.
And that I find it super powerful. It's a very long-term vision, and it can be as creative as you want it, but there's this long-term vision that's always underpinning it. And I think along the way, over the past 60 years, you mentioned a number of Nobel Prizes came out of JILA and NIST. It's really fundamentally connected to this. People take a very long-term view. People develop quantum physics because that's our division is called a quantum physics division.
Mm-hmm.
How do we use quantum physics to better perform measurements, to better characterize the standard, or design an entire new way or protocol to develop a new standard.
Mm-hmm.
And so that process has, I think, trained generations of amazing scientists. I myself is a product of this. I received my PhD here.
Yeah, let's talk about you and where you were born and how you went from where you were born. You mentioned a little bit, but you didn't go all the way back because you were born in China.
Yes, I was born in Shanghai, in China. And I came to this country when I was 20 years old. Actually,
what were the circumstances in which you left China to come over to the U.S.? How did that happen?
Yeah, that was in 1989. There was some student demonstrations at the time, and I was a little disappointed. I felt as a young person, you want things change faster. Mm-hmm. Economically, China was just opening up. Politically, China was.
When was Tiananmen Square?
Yeah, that's basically that time.
Oh, wow. So
I came right after. I didn't participate in Tiananmen, but I was in Shanghai. But
where's Tiananmen Square? What's that? Beijing?
It's in Beijing.
Yep.
Yeah. But so I didn't come to Boulder right away. I actually went to University of New Mexico,
which is also very active in the
in quantum,
in the deep science and quantum ecosystem and labs.
At the time, there was a famous professor called Marlon Scully. He was. He still is actually. Marlon is still active in quantum optics, and I became really fond of quantum optics, and I thought I want to study quantum optics under Marlon's direction, supervision. Mm-hmm. And it was in New Mexico I started to develop a keen sense of experimental physics, and I decided to come up here to work with Professor Hall, and that was in 1992. I came to see Boulder. And I did a 5-year PhD here and went to Caltech to do a postdoc. Mm-hmm. And by late 99, I moved back to Boulder to become a JILA fellow.
Mm-hmm. Great. Okay. Now is going to be the fun part for at least you and me. And let's talk about fundamental science, kind of how the world might work, kind of the edge of what we know and don't know. I thought this was a little silly. We'll find out. But in the big IBM announcement last week, one of the things they they outright said in their press release is that the quantum computing milestone that they hit also revealed evidence that we do, in fact, live in a multiverse. Okay, so let's just stick that out there for now. And let's talk about, in some of these topics you might be more comfortable with than others, but let's talk about how quantum kind of technology is used. Let's start with dark matter and dark energy. So dark matter and dark energy is believed to make up the supermajority of what exists,
Mm-hmm.
but we, as the human race, doesn't know what it is, where it is, what it does, what purpose it serves. So it might be as much together, it might be as much as 90% of all that exists. And the things that we see and sense is only 10%. And I think that some of the quantum, work that's being done is being used to try to unveil the mysteries of dark matter, dark energy. Is that true?
Particularly dark matter.
Okay.
And I think dark energy has something to do with cosmology, how the expansion, where does the expansion come from? So there's this dark energy, but dark matter has a very, very specific observational evidence from astrophysics, where seemingly that the galaxy, for example, where towards the edge of the galaxies, stars are still moving too fast and way faster than ordinary gravity would have be given. When I say ordinary gravity, meaning gravity from visible matter that we can see. And so people start to think there must be dark matter. And in fact, now there's a strong evidence that the universe is what it is because of the dark matter is underlying structure. And the visible matter gets attracted to dark matter. That's how we form all the galaxies.
So that's the structure, kind of scaffolding of the
exactly.
universe.
It's a scaffold of the universe. But where does dark matter come from? Is it associated with black hole? The only evidence we have of dark matter is through this astrophysical observation that we know exists through gravitational interaction.
Yep.
That visible matter, visible field interacts with dark matter through gravitational interaction. So either the gravitational physics is all wrong, which is very, very unlikely, and I think, or there existing this dark matter that we do not know yet how they will interact with ordinary matter like us, other than gravitational physics.
Mm-hmm.
Is it possible to see something that because of the presence of dark matter, that the known physics will be modified, and how do we search for such a signature? And so this goes back to the earlier statement I was making, by making some of the most sensitive instruments that we can construct, and we try to see, put multiple clocks made out of different principles. Recently, I don't know if you heard in news that we actually developed a nuclear clock instead of atomic clock. Now we can actually open up a nuclear physics to be a clock. And if you compare nuclear physics versus atomic physics, QED versus QCD physics, maybe will give us a signature of something that dark matter is coming in, interacting with our known physics, and provide some signatures for us to see. And this is really, right now, it's a fairly elusive search because we don't really know. We just don't know the nature of dark matter, but we can do some theory calculations. Suppose the dark matter belongs to certain mass range. We know the density of dark matter because of the evolution of the galaxies. So that number we know. And so if we say, okay, the dark matter has certain mass range, we can calculate how many dark matter particles are in there, what kind of field amplitudes this might be, and so on. And we can design our experiment to try to search for it.
Mm-hmm.
And that's a very meaningful. Of course, if we do find dark matter, it's going to change the paradigm of our understanding of the whole universe.
Yeah. And does something exist within that dark matter? That might be,
it may change the complete philosophy of our human civilization. I don't know, but it is something that we just don't know at the moment.
Yep. And so now let's talk about another thing we don't know, but that there's some level of evidence that comes out of string theory, that there's lots more dimensions than we as humans can sense. There's, we sense, 3 dimensions, 4 including time. But if the math around string theory is correct, there's more like 10 dimensions out there. And what are those 10 dimensions? Where do they exist? And potentially, I think this may be something that, isn't, because I'm not sure I've heard anyone talk about this, but is there potential relationship between these other dimensions and dark matter? Is that a possible?
That's absolutely possible. This is these extra dimensions unfortunately requires a lot of energy to unfold them if they exist, right? So, people talk about the traditional high energy physics where you build large scale accelerators. You accelerate protons into such incredible energy, you smash into each other, so you can knock out what's in there, quarks and so on comes out, and you study them, and you try to study what's the massive energy scale. The larger the energy you can give to these particles smashing into each other, the more close you're going back to the Big Bang. That's when the particles are being produced.
Yes.
And so if you want to understand the very basic fabric of the universe, you need to have this kind of a big energy. On the other hand, what quantum science is giving us now is that instead of putting billions of dollars to try to upscale these accelerator physics, also it's going to go out of the Earth's radius to build these accelerators. Maybe the future accelerator will have to go to the universe itself. The other prevailing thought now is to use quantum technology to build this incredible sensor to see if there's very minute indicators of symmetries being broken. Fundamental symmetry, like if I run time forward and backward, is this really symmetrical? You wish to be, because then we can always go become a youngster again. But in
Pretty
fundamental,
certain that won't prove to be the case, but I hope so.
We are just too complicated. Our human beings are just too complicated. But at a fundamental particle level, electrons, you move forward and backward, it should be symmetrical, and yet it is not. So at what level the symmetry is broken? Is the symmetry broken due to the unforeseen particle that's right there, that's being in the field of electrons, such that it's breaking the time reversal symmetry? Is that particle connected to dark matter? This is all very interesting, kind of a frontier topics now, where particle physics, high energy physics, start to connect to quantum technology, where to answer some of the most mysterious or deepest questions we have.
Yep. So let's hit the multiverse question, which to me, that's the thing that makes the least sense. And I'm surprised that it continues to get a lot of attention, because it's hard to fathom how that can be. I mean, there's almost so many paradoxes that immediately come of that. So the multiverse question, which is very related to trying to understand what's behind the 3 properties of quantum physics.
Yes.
There are some who believe that what's really happening is that when something is indeterminate, and it could be A or it could be B, to use your earlier example, it actually is A in one universe
and a B in the
and
other.
a B in another universe. So everything that is entangled, when the entanglement breaks, it wasn't that one of these possible outcomes popped into existence, another one just never was. It's that the other one also pops in existence, but goes off in a different universe. So you have these permutations of universe. And the reason that makes absolutely no sense to me is the discussion we just had. I mean, we can measure how much mass exists. We measure to a point where we even know we think we know there's this thing called dark matter, and how much of it is, even though we don't know it is. But no matter but there's no way kind of the matter we understand and dark matter, there's no way those can kind of hold, multiverses worth of things out there. So if the multiverse is real, it seems ridiculous. Yet as I said, even in the Google announcement last week, for whatever reason, they chose to include in there that this is, evidence that supports the multiverse, which is pretty crazy.
Yeah.
So where do you come out of that?
I actually didn't read that particular announcement.
It's on the press release itself.
Okay, I see.
Which is really bizarre if you think about like who would have approved that.
Yeah. I wouldn't. I personally don't take a multiverse very seriously, and it's partly because I feel.
In fact, if one of you guys are on the internet, can you look up the Google announcement that they made last week, and the
multiverse,
and then the language about the multiverse that was part of that, because it wasn't just this is evidence. It was a stronger statement than that, which is again why it appeared in that article or in that press release is bizarre all by itself. But why they
I wouldn't believe that. I mean, how do you prove? The very fact of a multiverse is it's actually unprovable because it's a parallel universe. It's in a universe that's living completely independent of our universe, and our universe will be bifurcating all the time. It's just like
all the time.
Not only all the time, but every aspect of it. It just feels like it's a mathematical way of thinking. Okay, you have A or B, therefore A or B both are real. It could be a mathematical construction, but I wouldn't say it's. If you want to say this is a physical reality, well, if we have no way of touching the physical reality, it's not a physical reality in my mind, and also it just feels it's introducing incredible amount of complexity into something
that's the other thing I don't like. It's
it's untraceable.
Or what's the one expression? Someone's Rockham's razor or something like that. The simplest explanation is the most likely. This is like the polar opposite of that.
That's the polar opposite.
The absolute most complex.
Yes.
Yet there are theoretical physicists, who still speculate that might be what's really going on. And the interesting thing about this this Google announcement was they positioned the choice of words to say this is a physical indication that is likely to be true, which is just bizarre.
I mean, people certainly do these so-called boson sampling, or there's all these. This is the whole point of quantum computing: is there's just incredible amount of a superposition, right? And in principle, all of those states are possible there, and you should be able to sample them and so on. But and that's certainly true from the statement of understanding the physical reality from this superposition, where in this particular copy that we made the realization of, and we would have to, in quantum mechanics, we often have to repeat those measurements often because it's in some sense there's a statistical nature built in there, and I'm quite happy with that level of understanding. Maybe you put a Bayesian approach into it. Like the more you learn about a quantum system, the less uncertain it becomes, and so you can actually kind of a learning, practical learning about these quantum systems instead of like it's bifurcating all the time, bifurcating in an unlimited way. It just feels it's introducing so much complexity that's not traceable in my mind. Well, I guess people can take the philosophical approach where, I have a multiverse going on. How do I prove that's wrong? Because I cannot observe that multiverse. So I'm not sure that's a reason. As an experimental physicist, I certainly do not take that seriously.
Yep. So okay, here's a good one to end on, and I think I might stump you on this one. Okay. So there are multiple reasons why I got really interested in quantum physics. Dating back to there was a book. The first book was God in the New Physics, which is probably 30 years old, and that probably triggered me. And then there were other ones that would be more recognizable. But one of the books I read along the way was from, I think it was Paul Davis, one of his many books, but it was a book about time. You know that book about time?
Yeah.
Okay, so we don't really know what time is, right? We kind of talk about time. We talked about time a lot in here. But when you try to pinpoint what do you mean by time, it gets the deeper you get in a discussion, and so here's my question. What is a unit of time, and how long does a unit of time exist? And the reason I ask the question that way is, I think the answer is, we use that expression all the time, but you don't really know what is the unit between this time and that time, or by extension, I don't think we really know what time means. What's your thoughts about that?
I tend to think of time as just a measure of how system evolves, and
So that's why I start with the unit of time.
Yeah,
That implies evolving from one moment in time to another moment in time.
Yeah.
So think of a moment
to
in time.
one state to another state.
What's a moment in time? How long is a moment? How long takes place between two moments?
Yeah.
And you start trying to address those questions, and it gets to like, well, we really don't know what a moment in time is. We don't know what happens between one moment in time and another moment in time. And I think there's something fundamental to that we use it so commonly. We use it, as measurement, but we don't really know, nor can we, we can measure time, but I don't think we can measure what a moment in time is relative to another moment in time. It's almost like there's a relativity there that is beyond our ability to see, like what changes from one moment to another moment.
Well, I guess that's connected to the energy scale. Like the larger the energy scale you can conquer or you can bring under your control, the shorter the amount of time you should be able to see that's elapsed. For example, the technology as we moved forward, before it was inconceivable that we can actually see electron moving around the nucleus. Now we can see that, we can kind of see that signature of it. Maybe in the future we can actually see how the nuclear motion is moving around. So the energy scale gets higher and higher, and the technology of being able to control that kind of energy will give rise to your capability of being able to see, dividing the time to a smaller fraction, and being able to see those. But I always think the time, as we talk about in a social convention, it's a human creation. It's we created time to have a sense of orderly life.
Sequence.
This is how we make a season. This is how we plant our agriculture. This is how we live our life. And indeed, the time is very conveniently defined. A second, a minute. It's very much a human scale. Yeah. Certainly, atoms don't live with that kind of time scale. And so fundamentally, time is there to govern how the system evolves and depend on large scale universe. And that's an unfathomable time scale for us to think about 10 to the 18 seconds. What kind of time scale is that? Or how small on a microscopic scale, how fast the nuclei can rearrange themselves to get to a new nuclear state, and so on. These are just completely different time scales that's needed to describe the physical phenomena.
Yeah, but where that breaks down for me is that implies that the deeper and deeper understanding we get to as a human race, that it's going to reveal, like,
yes.
Now, where it breaks down is what's different between one moment in time to the next moment in time. Mm-hmm. Like, what is different between those two? Because if you're in one moment in time, everything is a certain
exactly
way.
Present.
Yeah. And I'm talking about this at a universe scale level. What happens between one moment and the next moment that is different? And I have a potential answer to that, by the way. So what I envision in my head is that a moment in time is defined as nothing has changed anywhere kind of in the universe. Mm-hmm. The next moment in time is something has changed. And the something that has changed is an entangled set of particles became unentangled by this random nature of entanglement. So, what we're really sequencing, if you really thought about it as a universe scale, is we're sequencing. So, this is almost like using a word game, but, when I say what's different in one unit of time, another unit of time, and how much has elapsed, we don't know, like from a human sense and maybe from a universe sense, how long it took for one of these random de-entanglements, if that's word, collapsing of entanglement took place.
Mm-hmm.
It could be a long quote unquote time or a short time, but the difference in one moment, next moment is something happened, some of this random collapsing of a wave function somewhere between two entangled partners. So now at least one thing is different. And then it happens again, next thing is different, happens again, next thing. And that's the sequencing of events that make up, time itself. So,
and the time is not universal. There's no universal time in the universe.
But this would create kind of the universal concept of time, because wherever that collapsing of a wave function happened randomly, it did happen. You may not sense from your vantage point when it happened, but it was an actual event that created a different plane on the time field than the plane that existed. So you're really just waiting for that next.
But the entanglement
collapse.
Breaking here versus breaking near the black hole may be completely different.
What do you mean by that?
Because of gravity can come in and it can play a role of this quantum dynamics. We are not talking about quantum gravity and how the information gets scrambled. How when you say at one particular location of the universe, how the entanglement is being generated or being broken, versus at another place where the gravity is super strong, how the entanglement is being broken or generated. They could be happening at a different rate. And
a different rate, and that's what I mean. Like the rate is the difference between one moment in time and other, which is variable because you don't know when.
And then it's also true, if you talk about the entire universe, there are things happening here versus happening there. They have no way of communicating.
Yeah.
They also don't know. They really don't.
Yeah, they
know.
have no way of sensing each other.
Exactly.
But just like we can't sense a unit of time going from in an absolute sense.
Yeah.
Like you're in this unit of time, now you're in that unit of time. What might have caused that is this random event in a distant galaxy in a black hole. But anyways, that's just something that's gone through my head is like, what does time really mean at the fundamental layer? And I don't think we know what it means. I don't think we know what the sequencing of time means, which is moment to moment. What does it mean for time to go from, in a universe concept, from one unit to the next unit? What does that really mean? And I think there's, I think in that there's something about how the universe really works that we haven't quite, crossed yet.
I think you mentioned the string theory early on. In the string theory, even time is no longer continuous. So it's going to be discrete.
Discrete events.
Jumps. Yeah. And indeed. I think generations of human civilizations have been puzzled or fascinated by the concept of time. Everybody has your own philosophy, right?
Yeah.
And that's just because time is such a fundamental concept. Sometimes feels like it's invented concept, but it's also very deep, governing the evolution of the physical system, whether it's a universe or whether it's isolated quantum systems.
Because there's a synchronization that the universe is doing that we call time.
Maybe the whole entire universe, as some people say, is just within the bubble. It's just one particular Hamiltonian that's governing all parts of evolution. And we don't really know.
Yeah. So what excites you more? The discoveries about theoretical physics and how the universe really works, or the commercial application of quantum? My sense is it's more about the scientific, knowledge that comes from it as opposed to the commercial.
I think in my career that have been most excited about, actually, in fact, both. Maybe I'm not so much on commercialization because I'm not a commercial person. Yeah. But what I really am excited about is developing technology that's innovative, that has not existed before, and that allow us to open a new chapter of doing science. And that is the most exciting thing for me. I'm not a pure scientist just thinking about things, and so I like to do things with hands.
Yeah.
And I want to develop a technology that eventually can be useful, the ripple effects that can be commercialized for other things. But my main purpose is to develop the technology that I can allow me to see, open another layer of nature a little deeper.
Great. Well, thank you so much for doing this. This was so much fun. We covered a ton of ground. And,
yeah, great.
Hopefully, the listeners who really are starting to get into quantum, because of this, you gave them like deeper insights than they otherwise would have ever seen before. So I think this is going to be jaw-dropping for a lot of people.
Well, thank you.
Thank you.
Thank you. I enjoyed the conversation.
All right, fantastic.
Thank you for listening to this episode of The Bear Roars. If you enjoyed the episode, please like and subscribe on your listening platform. This podcast was produced by Loud Bear Productions and edited by Courtney Caruso with support from Kendall Weinberg, Emily Reed, and Gibson Siegert.